Let's get started. Welcome. Today we're very happy to have Dr. Alphonse Sterling from NASA Marshall Space Flight Center. Alphonse received his bachelor degree in physics from Caltech and PhD also in physics from University of New Hampshire. And after postdoc research at NRL and then Kyoto University, he was affiliated with NRL and then Marshall Center, but actually was posted in Japan, liaising on Yoko and Hinode projects. Currently, he's a solar astrophysicist at Marshall Center. So Alphonse is interested in various aspects of observational and theoretical solar physics, in particular the SPQs and CME, which he will speak more today.
Thank you very much, Hanli. Okay, hello everyone. Let's see. To begin with, some of the folks I've been working with on this project, in various permutations and stuff. Ron Moore, David Faulkner, Mitzi Adams, and Alan Gary. Okay, so I'm going to talk a little bit about solar X-ray jets. And X-ray jets have been seen since the Yoko days. As early as the very first observations, actually. So back in '92, we had the first papers on them. And Yoko saw them mainly in active regions. Now, Hinode was the successor to the Yoko mission, and it found solar jets to also be plentiful in coronal holes. And I can talk about their properties a little bit. I'll show you some in a second, but first of all, in coronal holes, the typical sizes as measured by Antonia Savcheva et al. Here are about 50,000 kilometers in length, extent, and about 8,000 kilometers in width. And they occur at the rate of about 60 per day in the two coronal holes. And they often have a hot loop at the base, which has been key to some of our interpretations of the way they operate. So anyway, here's a wonderful movie. This was taken from the Hinode spacecraft, the X-ray telescope and the XRT. And you're seeing the polar region of the sun over, a day or so, several hour time period here. And you see in the corona here several of these jets that go off. And so this is, I guess, highlighting one of the jets here. And here are some of them highlighted. And they're dynamic in time. They live an average of about 20 minutes, at least for this variety. Now, these numbers I'm saying are actually for the coronal hole jets. The active region ones have some different properties. But anyhow, if we get a nice, healthy one here at some point, one thing you can see is that the spire comes off in one place, and then off to the side you'll get this brightening. So it seems like you have the spire, and off to the side of one of the base, one of the sides of the base, you'll get a very bright point in the X-rays. Okay, so that's what these things look like. What can we say about them? Well, an often discussed mechanism is based on emerging flux. We all know flux is continually emerging from beneath the solar surface. So idea was put forth that this was driving these things. Now, the observations that are in the properties that I've summarized so far have mainly been based on observations prior to the SDO era. So SDO, of course, could see an EUV allow the coronal objects. Of course, we saw some in with SOHO EIT and some other instruments, but that didn't have the cadence and the resolution to really do these babies justice. So we do have now, of course, the AIA, which has vastly improved capabilities. And so one thing we've done is look at the jets First, we would make sure they were X-ray jets, and then we would look at them in AIA to see what more we could learn about them. So next, I'll give an overview of this emerging flux idea, and then talk about some of the observations. Okay, so this idea says that, it's obvious, first of all, that jets go on vertical magnetic fields if you look at their structure, the spire structure. But anyway, especially if you're talking about the coronal hole jets, they're obviously in a background open field. So in this case, we have a background negative field. And in this, we have a proposed emerging flux. Flux emerges. So, of course, there's a minority polarity here, the plus in this case, that comes into the dominant minus polarity background. Well, if you do that, then you're going to expect a current sheet to appear here on the minority polarity side of this. And when you do this, you get reconnection that can go on. And the proposal is that this creates two reconnection products. One is a new open loop, and another is a new closed loop. And the closed loop that was proposed is the bright point that we see off to the side. And the jet will come out here from this side along the new open loop, so opposite this hot bright point. This reconnection we'll call external reconnection, also known as interchange reconnection, occurring between the thing driving the reconnection, which is the emerging flux in this case, and the field external to that driving field, which is the ambient background coronal field in this case. So you get that reconnection going on there. You get a nice bright point, according to this idea, and a nice jet. Well, a lot of good folks have looked at this using numerical simulations, and it works really quite well and quite satisfyingly well. So it's remarkably fits, seems to fit the data quite well. So here's just one view from Yokoyama and Shibata sans. And so you have the emerging flux here, and you get the connection going with the ambient field. Nice hot loop, they call it this one. And then you get various jet details. So as I say, there are a lot of work has gone into this, a lot of wonderful work, and looks really good. So that was the original idea put out. But later, there was a further variation of this that was put forth. So this was done later, mainly in papers by Moore et al. The earlier work, of course, was Shibata et al. And Shimojo et al. Did a lot of really great measurements of jets, mainly in active regions. So anyway, what Ron Moore proposed was that there were two types of jets. By looking, and what actually Ron did this work, started it initially, and he looked, as he's very good at, he looked at a lot of data on X-rays, and he looked at these jets. And what he found was that jets seem to have fall into one of two categories. One, which I'll explain why in a second, called standard jets, and these have a simple spire that remains relatively narrow. And also other characteristics are the X-ray base has a bright point, but other than that, the base is pretty dark, basically. So you have the spire and the bright point, and that's it. And also, if you look in cooler lines, and specifically in the 304, which sees a lot of chromospheric plasmas too, you see little or no jet. So basically, you get the hot jet, hot spire, and you don't get a cooler jet. In contrast, these other jets, which you call blowout, and for the reason you'll see shortly, These, in contrast to this, had a much more complex spire that became very broad. It started out narrow and then broadened. And also the base tended to be very bright also. So the bright point's there, but then the whole base brightens up. And then these, statistically, the ones that were morphologically categorized into this blowout bin, had many more cases where you also got a 304 jet too. So it's, rather than going on this, just throw a couple of examples. This is a standard jet. So this is from XRT, and this is near the polar limb. But you're seeing this jet come out, and you see the nice spire come there, and a nice bright point, and this is pretty well behaved and doing its job. So you should have the emerging flux coming here and doing its business and making this baby. All right, there's another one, I think, right here. So same story, nice narrow spire, doesn't really get very big. The movie does cut off, but you get the basic picture there. Okay, then we can go to the blowout jets. And of course, those of you familiar with XRT data will just recognize this as an artifact right here. But again, we're near the limb, and we see here now the spire, but this time the spire becomes really quite broad with time. And we do get a very sharp bright point. And there is also additional brightening at this base here. So anyway, you're getting that broad spire. And here's another nice example where you get nice broad spire that develops over time. So these works put forward an idea for how these work. And this one is basically what are called the standard jets. And that's because it really conforms to this original idea that I mentioned earlier with the emerging flux making the jet period. And Ron dubbed this a standard jet because, well, if you call the 1992 models the standard models, the original ones. So anyway, you have the emerging flux coming out and making this reconnection here, as we just talked about. And then basically the action ends there. That's it. So it's made its bright point, it's made its jet, and it's done. Okay, in contrast, then, is this other beast, which is done in a slightly different way. In this case, the difference is that the flux that emerges is assumed to have much more a non-potential field involved. So it's a more complicated sheared feature that emerges out. So in this case, what happens is the reconnection occurs, and it starts out making a nice, normal, healthy, standard jet, and the bright point. But then it kind of loses its mind. This thing here, it has so much energy pent up in it that it becomes unstable with this reconnection, and it just blows out also, and it erupts. And this is why it's called a blowout jet. This whole base part erupts out and blows out. When you do that, you start getting additional reconnections here. That makes additional brightenings down here at the base. And so in the end, you get this very broad spire and a nice, your bright point's still there, but you also get additional brightening here at the base. So this is, in contrast to the standard jet, this is the blowout jet. So we have these ideas for these two things going on. Oh, I should also mention that actually Ron also presented another way by which this blowout jet could occur, and that is that even before this initial reconnection occurred, this internal bipole here explodes out, and then that runs up here and makes this reconnection, and you get all this subsequent stuff. So anyway, the same basic picture, but this thing is exploding and making the reconnection.
So I noticed that in these sketches that you show the jet going basically vertically up, whereas the observational examples, you can see that the jet has quite a distinct curvature. follows there be some overarching, maybe far-reaching magnetic structure?
Well, this one to me looks pretty vertical, or subvertical, if you will. But
But the other two,
okay, but nonetheless, it is a very true point and a very good point. This doesn't rely on it necessarily being a fully open field. The same sort of thing could happen on a very large scale loop also, but it has to be uh, quite large scale open compared to the size of these loops down here. So yes, you can get that on a loop structure too, and we think we do sometimes see some jets going off onto loops also.
yeah, so it would make one curious whether at the other end of the loop then something will be coming down.
Right. We think we have seen that sort of thing also, but I'm not touching on that now. But yeah, that is a good point. And yeah, we think that does occur too. Okay, so now let's do some AIA stuff. This is mainly from a paper we did led by Mitzi Adams. And we did some AIA and HMI observations. And this is an on-disk jet. And in this case, we didn't have X-rays for this. So we can't say whether it's an X-ray jet. It certainly is a coronal jet. But anyway, so we can see how this one is working. In particular, we can look for this emerging flux region source for the jet. So this is right to it. This is the jet. This is AIA 171 of it. So here's the eruption occurring, and you get the jet coming out right here. And let's see that one more time. And of course, we have the magnetic field here, as you can see, that there's the jet. And if we look at this same feature in 304, you also see the jet coming out. So, all right, let's see then, if that's the case, let's see if it's in an environment that is having flux emergence or some sort of flux changes that would be critical. Now, let's see, what do we have here? So this is a region that we were just looking at, and this is a box where we will look at magnetic flux. And so what we did was we looked here, and we looked over a few hours. The jet occurred at about 1300. So we start here at about 1130, and we look at the variation of the flux in that box. This is, as I recall, it's only one polarity. This is a positive polarity, because trying to get both of the polarities is kind of tricky business. So we picked a box and we tried to get an area that showed relatively little flow along, outside of the box over this period of time. And we measured the changes. And basically, it doesn't change very much at all. We put some limits on here. So, there could be some emergence or something, but, it's all down at the 20% level.
Flux is measured how?
It's just summing the flux, the HMI line of sight flux inside that box that I just showed you. Okay. So there's not much flux change there, but also, actually, Ron was really quite persistent with this. I was in Japan, and he was in Huntsville and working with Mitzi and doing everything we could to these magnetograms to try and pull something out. So to review it, I've forgotten the hours, but these magnetic fields here were integrated for quite a long time. Couple of hours or so. So anyway, we could get quite deep magnetic fields here, and we were looking for a bipole that might be pre-existing, and maybe that bipole may have just been disturbed before the jet or something to make it go off, even if you didn't have fresh emergence. So we looked for a nice dipole that would be in the region where we would expect it for this jet to form, above, and we just didn't see a convincing dipole of substantial magnitude at all. So again, at some flux level, again, I'd have to review, but with the summing, we got quite low weak fields in there, and we just didn't see a convincing field there. So, or a bipole, I should say. So instead, yeah, I guess we're ready for this. What I actually noticed, and we've been doing a lot of work with eruptions, especially Ron and I, over the past, decade or whatever. And to me, what this looked like was actually a filament eruption. I've just been looking at them a lot, and it seemed to me that this was also just a filament eruption. So if you look here at this thing, before the jet starts, you do see a small dark thing that seems to come out from this area. Maybe a 304 shows it even a little bit better. So just right here, a dark blob develops, then it comes out and goes along these field lines. And also you get a brightening too. And you get a brightening and it occurs right here. Well, to me, this just looks like it's just an arcade, or a filament arcade, a filament channel right here. And with the strong magnetograms, you can get the positive and negatives over in the right areas. And you get brightenings here. And of course, you get the brightest area, the brightest brightening where the field is strongest, just like we see with some filament eruptions in like quiet region areas. So to me, it's just looked like a filament eruption that was going on. So we went back and forth about this, and this is basically what we think is going on. This might be too confusing, but anyway, there are vertical fields here. Or it's available for having vertical fields right here, and we think this thing is just coming out of here and crawling onto these field lines. I think if we take a cross section of this, then it can show a little bit better in this sort of view. And this is actually lifted from a paper we did in 2001 for a real filament eruption. It was next to a sunspot and it had an open field configuration. So again, we had a closed, in this case, we had a closed filament encased in its, in its arcade field. Again, it's next to some relatively strong field, but next to it is an open field, and that's essentially the same situation we have here. Except, of course, there's no sunspot, but there's open field and there's this arcade field that is laying up against it. So anyway, in this case, what happens is this thing here erupts. Why does it take off? Well, by magic, just like all filament eruptions. We don't know exactly why, but we probably had some idea in this paper. I don't know. I can't even remember. But the point is, something causes it to lift off, as they always do. But what happens after that? Well, this field meets this vertical field, and it starts making new lobes over here, and it makes a bright flare down here, just like normal everyday flares. And that seems to be what's going on here, too. And let's see, do I show it here? Well, in the paper we do talk about that, but basically this thing erupts out of here. This is showing this, now the colors are reversed, but this blue is showing the blob, and it's coming over here and it's sneaking onto these open field lines, and we're getting the flare over in this area. And actually, you can see here, like from this is in, this is in 304, but you can see also from this frame to this frame, you get a lot more bright material. Again, the colors are reversed. You get a lot more bright material that spreads from this area out to over here as the eruption is taking place. And we think that this is due to these new loops being created as these reconnections are occurring. So in this paper, we call these things that we saw on the foot here EIT crinkles, because we saw brightenings in EIT. And then when we looked in SXT or whatever it was, whichever instrument we were using for the X-rays, we would see brightenings actually going from this middle part out to here. So it looked like there were really bright loops that were being formed transiently as this eruption was taking place. And we think the same thing is occurring with what we see here. Okay, so let's go at this for a second. So emerging flux isn't causing this thing to go off. Well, what is? So here we have magnetograms from the region, and this starts at 0 hours on this day. And again, the eruption took place at about 13 hours, which is about this time. And again, we had those strong magnetic components here. Yeah, I think it's this here where this bright flare is occurring, or bright point, if you will, is occurring. So the red here and the green there, and so very conveniently, this is changed over to these different colors. But anyhow, the point is, right here we have this flux, and this is still at 2 hours. So again, 13 hours is when the jet occurred. But 2 hours, you have this red here coming out or appearing. And this is the area where the jet occurred. And over time, this thing, now the arrow stays in the same place, but this red migrates upward and is apparently canceling with this blue here. So at this time of the jet, with 13 hours, the red is substantially reduced in size, and then by 15 hours, it's virtually gone. So in this case, it seems that flux cancellation is triggering the jet activity. Okay, so with this background in mind, we look at more events with AIA. And this, yes, I had to. It was pretty much at disk, very much on disk. Yeah, so 200 and 300. No, but yeah, I'm not worried about it, actually. Yeah, I think so. Yeah, right. So no, but we did not. Yeah. Okay, so anyway, so let's look at some more, and this is what we did in our latest paper on this stuff. So for this study, we looked at 20 jets. Actually, I looked at more, but this is what we reported. And we looked at XRT data. So we found these jets with, again, they're real X-ray jets. And then these were actually selected in the Moradel 2013 study. And then we examined the AIA data, and we looked at all the AIA data. Then at some point, we realized that the hottest channels, the 335, the 94, and the 131 weren't showing us anything much at all in the Spire, and they showed the bright point or something a little bit. So then we focused on just the 304, 171, 193, and the 211 channels. And so anyway, we looked at all these things. So here's one of them. This is the XRT. Nice, nice spire here. Nice, good, well-behaved bright point. And you'll notice here also that the spire is also moving away from the bright point as they usually do. But anyway, we'll get to that. So, all right, so now, of course, what we should expect here is some flux emergence going on according to the emerging flux model, and it's reconnecting here, making that bright point, and then spewing this jet out. So let's look at 193 and see what it says. This is the 193, and we can see a lot of complicated stuff, and you can even see the bright point, but you do see this dark material, this absorbing material coming out of this region, and it emanates from this place exactly where that bright point shows up. And then it goes through complicated interactions. Seems like the jet doesn't fully, I'm sorry, I'm going to call this a mini filament. This mini filament doesn't, part of it goes away, part of it doesn't. But anyway, the point is it comes out from this region and it interacts with some of the ambient field, and in X-rays it's making that jet and the bright point.
They overlap in temperature somewhat.
193 and XRT, no. I can't recall if 193 has a hotter component, but XRT would see this would be up around 1,000,000 K, plus or minus a little bit onward, and everything hotter than that. Yeah, that's right. Right. And they have. Yeah, and I was trying to recall what is the temperature of the hotter component in 193. Yeah, right. So you'd really need a real flare. No. It's also you can't see the filament material too. Right. Yeah. Now, to the well-trained eye, sometimes we can't see in the X-rays things. Oh, there it is. Yeah, it's there. But yeah. Well. Yeah. Anyway. Yeah. So here's one at the limb, and again, nice, very well-behaved spire here, and also well-behaved bright point. And 193. See if this one is any more better behaved than the other one, showing a nice emerging flux. And it seems to be even worse. It just doesn't know how to operate correctly. But here we do get a very clear view, I think, of an eruption going on. And as I say, I've been looking all these years at eruptions. It looks like an eruption to me. And it comes exactly from the place that the bright point shows up. And it's really interesting because sometimes you can't even see the bright point in the cooler channels at all. And there can be other things that are equally bright, and also it can be hiding behind some of this absorbing spicule forest. So like here, if you're looking at only this, you can't be positive. Well, maybe that is the bright point there, but maybe it's hiding under this absorbing thing actually. But it's very stark in the X-rays. So really, the combination I think is needed to really sort this. Okay. So how about this one? This one, the XRT is not very long, and of course this is an artifact, this black thing here. But there's a very distinct bright point, and there's a spire that comes out. And the 193, and this is another case where the bright point I think would be hard to identify in only the 193. But you can definitely see some cool material coming out. So this is now, we're back to a normal eruption from trace, one that we analyzed in some I don't know, a long time ago. But anyway, of course you get the filament erupting, and in this case, no one's going to dispute it. You get a nice flare loop. That's just a flare. And of course, as we've seen many times, and many other people have, the filament starts its activity before the flare actually begins, which is also very similar to what we see in the jets. Okay, now we've talked about this, and we talked about this blowout jet and standard jet business. All the examples I've shown you so far fit into the blowout category. Well, what about these standard jet things? What are they? Okay, so here's an example of one that was categorized based on the X-ray morphology as a standard jet. So a nice, relatively thin spire, and you get a bright point. there. So 304 is, I looked at these, of course, in all the wavelengths, but I selected the ones that I thought were most representative or showed best the points for each case. And here's the 304. Well, here it's kind of boring. It just doesn't do too much, but it does do something. And what I think is going on here is, well, I guess we can come back to it in just a second. Let me go on to this. This is another normal eruption. But it's normal, but it's not ejective. This thing starts to take off, and then it fails. So this is one of our failed eruptions, a confined eruption. So it's no doubt what this is. This is a filament erupting, and it's just not getting out of its overlying field, and it's making its flare down here in this area. And if I look at this seems to me to be a very similar type of thing. You're getting some sort of disturbance starting down here, and again, I think starting down here in the area where the brightening actually occurs over here. So at least in this case, I think the standard jet is a result of a confined mini-filament eruption. I must say that I think in other cases I looked at, it's not quite as clear-cut. There are some cases, for example, where I think there's also a mini-filament eruption going on, and I think it is an ejective one. But in this case, for whatever reason, it just doesn't have enough momentum to carry it very far into the far side fields. So it remains narrow on things. And remember, it was identified as blowout or standard based on the morphology. So there might be different reasons for it to come up with that morphology. Yes?
So, for example, in this case, then the jet represents, you think, you've got this sort of combined thing, but it's squeezing and creating the reconnection that gives you the jet. Along the lines, it's not necessarily merging flux, but it's giving you the reconnection that's giving you the jet. Like you showed here earlier.
Yes.
So my question is, when you have a confined flare,
Yes.
confined filament eruption that goes up, do you ever see anything on a larger scale which like that?
Right.
Like the
Well,
jet itself, yeah.
right. I remember dealing with that question. I can't remember what the response to it was, but offhand, I can't remember a jet due to a confined filament eruption.
It might be harder to see if it's bigger, right? It doesn't have
Yeah, right, and that could be the case. And
But does it make sense that the cool material stays confined and some of the hot material escapes?
well, let's have a bit more look forward and see what goes on about that and readdress that. Okay, so anyway, I'll say that for now, and I'll also say that I think that again some of these are basically the other type too. I think when I draw the cartoon, I can say this a little bit better. So let's get to that. Okay, so first of all, of the 20 things that we looked at and we summarized, again, as I said, I did look at more of those, but all of these showed material ejections ejected from the location that brightened. I should say that all of them showed this. All of them either showed this or they were consistent with it. There were one or two cases, one I remember very distinctly, where it was all in the same line of sight. So it seemed like the filament eruption was coming, and then you had the bright point, but they were aligned with each other, so you couldn't see the sideways geometry, for example. And then there were a couple of cases that were weaker. We had our poor cases, but those were about 3, I think. But they basically all were consistent with this or very clearly showed this. Over 18 cases we did the average size, and this the size of the mini filaments was about 8,000 kilometers, and standard filaments are larger than that according to the standard literature. So from about 30,000 kilometers. So that's why I call these mini filaments. and they have a pre-eruption velocity of about 30 kilometers per second. But anyway, one more point about this 8,000 kilometers. If you recall the Savcheva et al. Studies, they also found that the average width of jets was about 8,000 kilometers, which I think is a nice, interesting consistency in these. Another caveat I should say is that all of these cases were polar coronal hole events. So not active regions or other regions of the sun. So that's what we're looking at here and talking about. Okay, so we're ready now to get to this picture, and maybe some of the questions I may have forgotten might come up again here, and I can address them again. Anyway, this is a picture just showing, of course, the bright point and the jet, and then the AIA of the filament coming out. So this is a picture we draw of it. It seems like all of these have this sort of geometry. We have a larger loop, magnetic loop, next to a smaller one. And the smaller one is charged. It has non-potential geometry, and it has a filament sitting in it. Okay, now we might think, well, does this make sense? One thing is that you could think of this as just having a positive polarity inside this negative background. And in that case, you would have field that could splay out in all directions. Or in 3 dimensions, it would be an anemone region, where you have this the positive in the middle and the shell of negative all around it. And it all connects to this background negative field. And here you're just taking a cross-section of it. And then one part of this anemone fan happens to be charged up. And so you can get this sort of geometry quite naturally. And then, okay, so magic happens again and causes it to erupt. I think we'll address magic a little bit later. But anyway, whatever it is, it causes this thing to start going. And when it does, what happens? Well, it's kind of cool actually, because right here, as long as it's on this side of this bipole here, this neighbor, it's not going to do anything because the fields here aren't going to allow it to reconnect. So it's just going to go for the ride, and it's going to ride this way. But then, when it gets to the other side, it's in trouble because it's going to run into opposite polarity field. And then you're going to start to get the reconnections. And that reconnection is going to brighten this loop by adding new loops here, and it's going to add a new brightening here. And this reconnection here, that's going to be what's going to lead, we believe, to the hot jet. So this is the hot jet here coming out. And then, if this reconnection continues far enough, then this will eat away the surrounding field around the filament until the poor filament's there all alone, and its field lines start reconnecting, and then the filament material also is going to start flowing up. So you're going to get a cool jet too. So what about this blowout and standard business? Well, all right, first the blowout thing. This is a blowout case because here the reconnection has gone far enough, it's going to start plowing over into this side, just plows over and it keeps on plowing over and it reconnects and it makes like a broad jet going, over several field lines here. And the cool material gets out early, so you get a cool jet too. So the blowout, quote unquote blowout jets will have cool material that gets onto these field lines and also escapes out. So the quote unquote blowout jets will have more frequently the cool component also showing up. Now the standard jet. So in the standard jet case, this just doesn't have enough energy to do this. So it's confined one way or the other. And in this way, it just gets enough to make some reconnection. Some of the outer shell is going to make some reconnections. And then it's going to it's going to make the hot jet here. But this blue stuff isn't going to get onto that field line. So if it, in that one that turns around, it's a little bit more complex, but it might be this sort of thing where it just sort of comes over here and just sort of rolls around get some reconnections going on this hot field. So in a way, someone asked about that. Yeah, and I guess the answer to that, yeah, Sarah, the jets, and the large-scale filaments making jets. I guess the analogy would be this. In that case, if you had the overlying fields closed, then you would get an outer shell that is actually brightening. And so I think that's what we would have to look for and consider, rather than necessarily, because it's not an open field necessarily.
Yeah.
Yeah, so I haven't looked for it in that context, but I think that's the one we should look for.
If you had a filament erupting that was near a coronal hole, say, you might
Yeah.
conceivably get this
Yeah.
property in the same way
Yeah.
on a large scale.
Yeah, right. Yeah, right. And there are, well, that's for future work too, but yeah, I mean, surges and the like. Okay, all right, so how about on disk jets? Time is moving on. What's wrong with it? It's a mess. Okay, anyway, we didn't look at on disk jets in this study, obviously. I did talk about the Adams et al., where we did do that, and it's basically consistent with this mini filament eruption picture. But others have seen this too, actually. Now that we look back at it, a lot of good folks have seen this sort of thing. There are also other works that didn't have like the good, the AIA. These had, well, not Wong et al., but anyway, these had AIA, for example, and they saw similar things. And these, Raffaele et al. Had only X-rays, but they had indications that they were eruptions that were making the jets. And Nichio et al. Were looking with, I think, stereo, so they didn't have the resolution, but they had results I interpret as consistent with ours. Here's a very nice view from Shen et al. And this is a non-disk jet. It's very clearly a filament type of eruption going on here, and making the brightenings at the base. So, okay, so that's that. And so we might address, well, what might cause these mini filament eruptions? Again, we didn't do it here, but in addition to the Adams et al., which I already said was, we felt flux cancellation, Huang et al., Young and Mugla, a couple of, in 2 papers actually, also found cancellation to be the source of on-disk jets. They weren't looking at X-rays, but they saw the AIA jets. And then other studies found cases where there was emerging flux, but there was emerging flux and cancellation going on. So you had emerging flux, and then I can't remember which one, but one of them said distinctly they saw emerging flux, but the jet occurred when the emerging flux canceled with the already outside neighboring flux. So our view is that almost anything can get these things to go, but they go in this sort of geometry, and the key thing is that it's a mini filament eruption that is causing these jets, and emerging flux isn't really an important point to it. Okay, this just very quickly is another paper. This was given by Ron in SPD or something, so I'm going to recuse myself of the accolades in here. But anyway, let me just get to it. He does the blowout and the standard. But anyway, the question here is what the spire does when you get these things going on. How does it drift compared to the bright point? So here in the emerging flux idea for standard jets, you have the emerging flux come out, and again, you're getting this interchange reconnection, and the spire comes out. There's one spire. Okay, there's one. And the bright point's over here. But then the second one is the second reconnection is going to be here with this next line, or this next line. So this is going to be the next line that brightens. And then the subsequent one. So it's walking toward the bright point with time. And he makes the same argument, with the blowout jets. Again, it's going to walk toward the bright point as time goes on. Now, with the mini filament eruption idea, so let's do that with well, okay, this shows it quite nicely though. So again, this thing is erupting out, interchange reconnection occurs, and you get a couple of these that are illuminated, but it's this eruption this time is going this way into this stuff. So you're getting the next one to occur, but it's away from the bright point. And then at some point, the mini filament becomes arrested. But the point is you're walking this way away from the bright point. And this is even more clear, I think, in the blowout idea, where this thing just plows far into the side and the brightening walks away from the bright point. And Antonia Savcheva et al. In a different paper, I've forgotten if he mentioned it here, but Savcheva et al., this paper, they found that the spire drifts away from the bright point most of the time. And so Ron's conclusions are that the mini filament idea fits the data better based on this examination. So just summarizing all this business, we observed for this particular study, Sterling et al. 15 this was, but we observed 20 jets in polar coronal holes with XRT and AIA. And we find that the jets are due to eruptions of miniature filaments. And they're scaled down versions of large scale eruptions where the jet base that bright loop corresponds to the flare. So there's just a flare. And the drift of the spire with time is consistent with the mini filament idea. Roughly speaking, the blowout jets correspond to ejective eruptions and standard jets to a arrested eruption or a confined eruption. For some of the on-disk UV jets, the mini filament eruptions result from flux cancellation. We cannot rule out other causes, flux emergence, but I just haven't seen it that much. Finally, we think that there are some possible astrophysical implications for this. The thing is, the emerging flux comes out of the sun. We know that. But apparently the jets that are made, the X-ray jets, aren't made by this. They're made by something else. So the thing is, why doesn't that, this emerging flux has to come out into this ambient background polarity. One of them is going to be the wrong polarity, and it's going to reconnect. Why doesn't it make this hot bright point? Well, it must be that this reconnection is occurring more easily or more rapidly or something than we expect from the models. So it just doesn't build up a strong enough current sheet in order to build up a nice bright point there. We don't know why, but it seems to be the case. So I think this is a question that we have to work with the modelers to try and sort out. Is there something that is fundamentally not understood, or do we need more observations, or what? And I'll close with that. Thank you.
Please show me again the smile with the magneto one.
Okay, probably you mean like this one. Okay.
The red and blue.
Oh, the magnetograms. Okay, yeah, right. Yeah.
So you have several hours in these images.
That's right.
Okay. I would like to do two suggestions.
Mm-hmm.
The first is the statement. In this case, instead of emerging flux, have canceling flux.
Mm-hmm.
You can have canceling flux with an emerging loop.
That's true.
So
We don't see it.
why?
I don't know. It's not there. We did see it.
Here is my
Yeah.
suggestion.
Mm-hmm.
You are showing line of sight.
That's true. That's true. I agree.
And
Yeah.
you have hours. You have several
Yeah.
electromagnetic field data
Yeah.
from HMI.
Yeah.
So you can
Yep.
you can go further.
Yeah.
And you can determine
Yeah.
exactly.
Now, is
what it
Vector going to be sensitive enough to show up in these quiet sun regions?
Sorry?
This is quiet sun.
Yes.
Okay, and it's going to be, even though these are down to, I don't,
Yeah,
let's
what we
see,
don't have maybe there is properly there is some deviation.
these are like 10 and 20 and 30. This is down to like 50 Gauss in the bluest and the reddest. So we're going to do it.
It's in the limit. That's correct. But I encourage to use the electromagnetic field if it is available, especially when you can determine what is the loop doing, what is the topology and the dynamic of the loop. This is what is going to tell you if it is emerging, submerging.
Yeah.
What is the cancellation? The cancellation is just only a observational path of two polarities getting closer. But it's not telling you if it is submerging or emerging.
Yeah. Okay. All right. That's true. If it's doable, I agree. That's a very,
It's in the limit. Maybe
Yeah.
It's in the limit of the signal, but it's a pity that having
yeah.
the electromagnetic field you don't use.
Yeah. Okay. Very good.
Use the stereo quadrature thing to do some stuff that's not at the poles.
There have been some stereo things, but these things, remember, the resolution is, these are, we're seeing these things kind of at the resolution of AIA. So stereo is going to be, and also the time cadence of stereo is a problem too. It's 5 minutes, if that's what you're asking.
No, but during quadrature they ran much higher.
Then that might be a good thing to check.
Low, high signal to noise observations that they didn't run.
Yeah.
Davina Innes has studied those.
Yeah.
They published 3 or 4 papers on what he called mini CME.
Yeah. Well, we certainly know of her work, but it's true. I probably didn't investigate it enough to see that they had high cadence stereo at that time. It was very good. Okay.
Rapid it was. It was double or 3 times the normal.
Still won't.
And it was higher. It was the highest resolution, and it wasn't compressed as heavily. I have all the data on my disk.
Okay.
So the Shibata and Yokoyama model showed a cool, they had a cool jet
Yes.
that went along with that.
Yes.
So I'm not sure why the standard model doesn't have a cool jet. That was part of the.
That's that's a true statement that you're making. They did talk about a cool jet being a byproduct of their activity. This is in the this is from the theoretical view of it, it's the interpretation we made in the Moore et al. Work. The observation is that these spires that stay narrow usually do not have a cool component. That's the observation. Now, and Shibata et al., now Shibata-san, of course, has done much work in this too, and he wasn't worried about, I think, whether, these jets are occurring. This is a basic picture, and okay, and then there's some wrinkle about it blowing up or something. So he wasn't worried about that. I do know that he has done work, I guess, with Brigitte Schmidt et al., looking at the hot and the cold being next to each other or near each other. So, yeah, that's right. So that has been seen in the jets he looked at, but he wasn't, didn't have in mind standard and blowout. That terminology came from the Moore et al. Work. And their observations of the narrow ones say that they usually do not have them.
Right, and given that 2D model, that was material entrained along the field line, right? You're hypothesizing this material transfer.
That's right.
Interesting, the observational ways to distinguish that observationally in terms of the relative location of the hot and cool material.
Yeah, and I think that is going to be intertwined, actually, at least in a lot of cases. Yeah, there was talk about that, whether it's next to it and stuff. I guess it could be next to it sometimes, but I would think that a lot of times it would be intertwined.
I think that their model had it more on the outside.
Yeah. Yeah, that's a good point. Yeah.
Well, I was just wondering if, from the large-scale filament down to the scale you're looking at, if you take that argument further, I'm just wondering if you've looked at scaling.
Well, it's an interesting thing. Ron led a paper 2011, I guess, where he argued, guess we had some debate about that among ourselves, but he did argue, and he argued, very cogently that if spicules work like jets do, then there could be enough energy to power the corona, including a lot of it in, like, for example, alpha wave flux, which hadn't been considered before in the previous back of the envelope calculations that we, and going back to the Becker's days, people didn't consider when looking at spicule energies. In that case, before, historically, there has not been enough energy for spicules to heat the corona. But Ron's idea was that they work this way. They also have a lot of transverse momentum. They have much higher kinetic energy than the classical spicules because of the type 2. Anyway, there are a lot of details there. Point is, it might be on the edge of possibly doing it if spicules work like jets. The thing is, when Ron did that paper, he had in mind a slightly different picture of the jets. So we'd have to see if it carries over to this, but it might.
So, apparent velocities of the jets, are they different in the two classes of jets that you have described? And if they really go way out, for how long would they be identifiable? I mean, how far away? And how would that velocity relate to the fast solar wind?
Okay. Well, I don't think I can address any of those, but let me start with the first one I can't address. We have addressed it, but I can't remember the results. We did it in a paper of Pucci et al., and we looked at, but it's very low statistics. We looked at one blowout and one standard. I remember that blowouts were hotter and much more energetic than the standard. I believe the velocities were higher, but I'm sorry, I don't want to quote. I can't remember them exactly. I think though the blowout was a little bit faster. How far out they go? We've looked at the edge of the AIA field of view, and they go that far. Okay. Oh, also there are some we know do make narrow CMEs. We've seen that with a subset of them. Actually, I just saw a new paper too that related a jet to a CME, and one that Ron Moore led in 2015, I think, looked at. That was kind of interesting, actually. He looked at, in that particular paper, what we did was look backwards. So first we found these narrow CMEs, then we saw the ones that corresponded to jets, and we looked at those jet properties. And what he argues is that the ones that tend to make the CMEs have more twist as they're being launched than do the ones that, than the average. He didn't actually measure, to do the full one-to-one, but he had an average for how much twist these jets have, some measurement of it. And then he found that the ones that made largest twists tend to have these CMEs. So some of them actually get out to the heliosphere.
Yeah, in that context, briefly, example of a detailed observation you showed where the eruption kind of failed. You were saying it was just rolling around. That to me looked like there was some way a release of torsional energy that was stored.
Yes. Right. Yeah. Going back to, it's not the right picture, but Shibata and Uchida, for example, talked about you have twisted flux rope down below, and it erupts and reconnects with the open field and sends its twist from that torsional, previously closed field to that open field. And we think that this picture is going on here. i.e. we think that in our, obviously this is charged, it has shear in it, and so it could have twist in it. And this twist could be what's making these jets that we observe spinning, and others, observe spinning, makes them spin. So
Also make for lots of altitude.
yeah, that's right. That's exactly right. That's exactly right. Yeah, yeah, yeah. And in fact, in that paper I just was talking about, Moradel 2015, the argument put forth there is that it's crude, admittedly, but it's I think interesting. He talks about the amount of twist that is on the jets initially, and he measures that to be something, in some way. Then he tries to measure an estimate of twist that might be on these narrow, what do I call them, narrow CMEs out here, and you can't see them twisting, but you see them waving a little bit. And he measured that amount of waving, and he argues that the amount of twist energy has gone down between here and here. Where could it have gone? So anyway, it's an interesting idea, I think.
In all the sketches that you showed, you had a basically uniform overall magnetic fields. That would fail if you were near the polarity inversion line. Could you have jets near the polarity inversion line? Do you know anything about that?
Well, let's see. Here's kind of a jet, right? It's coming out, well, it's not an open field, but
The overall magnetic field has opposite polarity on the two different sides. That would be polarity inversion line.
oh, you mean in the background coronal field? Yeah, if there's another positive over here, you mean?
Yeah, right.
We haven't. I don't think we've dealt. No, we haven't done anything like that.
Maybe they don't even exist.
Would it be confined by that overlying loop?
Or yes, they could either cancel or
Yeah,
cooperate.
yeah. Well, have to think about that, but yeah.
In this new topology configuration you're considering, it seems that all these flower jets involve two neutral lines.
Yeah,
So
yeah.
you will always see two neutral lines. So,
Two neutral lines are one circular one.
so maybe it's a statistically better relation.
Yeah, right. Okay. Well, throwing the magnetogram in there is a nice savvy hook there, because I can't say my smart aleck answer was, well, there are statistics. They all have two things come out. No, but you're exactly right. You're exactly right. I mean, we do need more undisc studies of these, looking at the magnetic field evolution, and yeah, that's right.
You always see that the cool material come out before that right point.
Yeah. Well, I have to be careful because I'm biased in my thought. So, well, let's look and see. Well, they don't line up exactly, so it's kind of hard to say. Yeah, yeah, right. So, I do have to be careful because I have my feeling for what it is. So, I guess I don't want to address it.
Probably with DKIS running
Yeah,
all these
yeah.
fantasy field line configuration can actually be observed.
Yeah, I'm 100% for DKIST. Yeah, I mean, I think that we can see a lot, and in fact, I was just chatting with Kevin too yesterday. But DKIST is wonderful, but obviously it'll have a limited field of view. But
You have to have certain case studies.
yeah,
I mean, for this kind of scenario, the field of view is fine.
exactly. So we could perhaps see full eruptions in this sort of field of view in these jet cases. Yeah, I mean, you have to look a lot to get it to work out right, but eventually it would.